So, what were we doing with this last time? It was Monday, a couple hours ago.
We were discussing the linear modeling of y equals slope times x.
Love it.
Y-intercept.
Thank you, Tori. We had a linear model based off of this. What was our linear model? What did it end up being? Y equals, numerically, what was ours?
It was
9 mil over 8 years x plus y-intercept, and our y-intercept ended up being 32.75 mil.
Thank you so much. 7.5, you said? Perfect.
X equals 23.
Brother, how are you? Hey, buddy. Good to see you. Good to see you.
Oh, it's cute.
Here's a linear model. Eric Magnuson, great CIS instructor. Good guy. Hell of a drummer, too. Hell of a drummer. Here's our linear model. Now, that in and of itself is great, but I like to also see something else with it. So, Tori, the way you said it was perfect. You said it beautifully. You said X is number of years since, I think it was 1990, right? Yeah, years since 1990. And Y is uninsured in millions. In millions. Under age 65, no health insurance. I'm distilling that down to just the word uninsured. It's okay with you guys. This needs more ink. Now, two crucial elements of that equation that we had to find were the slope of 9/8 and the y-intercept of 32.75. Let's talk about those individually.
So we did that.
Say that again.
Didn't we do that? Because I have y equals 1.125.
Which is what?
It came out to 58 million.
9/8 is about 1.125. Actually, it is 1.125. Not about. It's
Times
equal.
23.
Well, hold that thought. We're going to get to that point too. What does that mean? Yeah, this is the slope. This is a slope-intercept model. Can we see this on the camera? We getting the equations too?
Are
Kind of.
you wondering how we came up with those
No.
numbers?
I know how you came up with it. You used good algebra.
Yeah.
You used the algebra you used in Math 60 and Math 65 and probably Math 95. That's awesome. But Crystal, what I want to know is, what does that number mean?
Millions of people increase per year.
Say that, Andrew, much louder.
It's how many millions of people increase per year.
Did you hear what he said? Say it again, louder. In the back there, right? Raquel can't hear you.
How many millions of people increased per year?
So, it's a rate, isn't it? It's a rate. When you see 1.125, what that means is we increased, and I'm going to throw in, if I may throw in two more words. On average, 1.125 million folks under age 65 in America per year. And I'm focusing on those four words that I underlined because they're pretty important if you think about it. Right? They're pretty important if you think about it. On average, per year. I'm not questioning how we got the numbers. As a matter of fact, we're going to automate how we get the numbers here momentarily and let the machines do it for us.
I already did that.
Say that again, Crystal?
Well, I already did that.
Well, good for you. And you probably got a slightly different value than we did.
Oh, it was really close.
It's really close, but it's not exactly the same.
Oh, yeah.
And this is where we start crossing the line from estimating everything to getting a little more precision using technology. And that's what we're going to do in the last couple minutes of class here. So here, I want to break down this statement first, though, okay? We increased. How can we tell we're increasing? Don't look at the chart. The chart tells you we're increasing because it's going up. How can you tell by the number that we're increasing? Ryan, help.
You go up 9 over 8.
Good, he's thinking slope. Up 9 over 8. Could we go left 9?
No, because it's not there.
Careful. Could we go left 9?
No.
Yeah.
Good.
Yes.
That's
Yes.
As long as we go
Down.
down. Right. So we have negative, negative, positive, positive. Right. What you're saying, why, you're going to ask me, Rule, why would you do that? Well, I wouldn't. I would do exactly what you said.
The line extends.
Because the line, technically, this is a line. This is 5 data points. More on that in about 20 minutes. Thank you, Tori. Perfectly. So we could take that line and come backwards with it.
Yeah, and then you find out what happened in year 88.
Exactly. Down 9 over 8, down 9, left 8, down 9, left 8. That still implies a rise left to right.
Yeah.
But more logically, Ryan's up 9 over 8, up 9 over 8. Way more logical, right? Good. Is that what you guys were going to say, Micah and David? Same thing? Perfect. Just the number itself is positive. That either means a positive 9 over a positive 8 or a negative 9 over a negative 8. If it's a negative, one of the two would be negative. So, good. So we know it's increasing. 1.125 million is a no-brainer because it's right there. But you have to catch the per year. You have to catch that. And it's important to start learning the on average part. Why am I making such a big deal about the on average part?
It's not exact.
Because it's not exact, because it's a best fit line. Good, actually it's a better fit line. It's not quite the best fit line, we'll get to that momentarily. But yes, what we're doing is we're sticking a line on that equation, or on that data, that fits it, if you will, the best. So what we did in class last week, I think, how did we used the two endpoints, right?
Right.
So we went from this guy to that guy. Pretend that's a straight line. Actually, no, don't pretend. Let's see if I can draw a little straight.
You need a yardstick.
I do need a yardstick. There. Now, believe it or not, that is not the best line that fits the data. This is. Hang on. Right there. That right there. I can't quite get it exact. That line is the best line. In other words, the best line that fits the data is actually not quite as steep as ours. Its slope is about 1.05, not 1.125. And its y-intercept isn't 32.75, it had to be 33.1. If you're shallowing the line, the y-intercept's going to come up. Okay? Now, don't write that down. You're about to find it using your TIs. You're about to find it using your TIs. Maybe you heard what Andrew said over here. He mentioned a best fit line. That is the best fit line. The best fit line is that red guy right there. Now, what does it mean to be a best fit? What do you think that means? Best fit.
The fits between the data.
Say that again. Nice and loud, Linda.
What line fits between the data?
The best. Now here's the deal. Here's the deal. Back to the original chart. Let's fly back up here again. Okay, back to our original data. There are lots of lines we could put on this screen to stand for the data, right? Lots of lines, right? We could connect these two. Say, let's use those. Now, good, some chuckles. You start chuckling because you realize right away that's not a best fit line. That's overestimating the severity of the slope. Because we picked the first 2-year increment when the slope was actually steeper than about 1 per year, right? 1 million per year, fair enough? So you don't want to use those two. Well, let's use these two then. Let's use those two. And you realize right away, that's not going to do a good job. How come? How come, Micah, help me?
It's not steep enough.
It's not steep enough. That's too shallow. That's got a slope of 0.5 million per year, half a million per year. So we could make using any 2 points whatsoever, we can grab any two. There's going to be 10 ways to do it. If I choose to, we'll learn that in this class as well. 10 different lines you could possibly throw up there by connecting 2 of the points. But guess what? Even if you used all pairs of 2 points, none of those is the best fit line either. This is the best fit line. Right there. That's the best fit line. How many points does that line hit?
None of them.
None of them. How the hell
But centers them.
can something, hold that thought, Tori, how the hell can anything that doesn't hit any of the points be the best fit line? Tori, what'd you say? Go ahead. Please.
It's an average between them. It's centered.
Good. But if I was to tilt this line a little tiny bit, it would still be centered-ish, right? So why is this one centered so perfectly? Now, this is a very tricky question, just so you know.
It projects out the data further.
It has nothing to do with the data that we don't have yet. We're going to come back to that, too. Thank you, Andrew. Please, Jordan?
It's not on any particular point.
That's right, but why is that better than actually catching a point? And I'm not saying it can't catch points, it just in general it doesn't.
It's right in the middle of all.
Because that's how you get it closest to each point.
That, right there, did you hear that? On average, here, check these out. See these little distances right here? Those are called residuals. In Matthew 44, we'll study those a lot. Not so much in here, because we're gonna let the TI deal with them for us. The sum of those residuals, if you make it as small as possible, That means your line misses the points as little as possible. Does that make sense? So that's why when we had the line going like this, let's grab the color here. When we had this line going, yeah, there's absolutely no residuals between the first and second points. But then the problem is, as soon as you get into these points, there's ridiculous amounts of residual, right? So that's clearly too steep. Same thing with too shallow. Sometimes the lines will go above and below the certain values. But at the end of the day, the one that fits the data the best is the one that misses, on average, gets as close as possible to the data, and misses it the least. So this is called a best fit line, for sure. It's called a best fit line. A best fit line. And we're going to keep referring to it as that. The best fit to the data. If you guys in later math classes do something similar to this, you'll very often hear it called a least squares regression line as well. A least squares regression line. And the idea of least squares has to do with how the computation for that line is done. If you were to do this computation manually, it looks like this. It looks like that.
Wow.
And it's horrendous. 25 years ago when I was learning this for the first time, that's all we did. It would take us like an hour and a half to get through that. You take each x and y coordinate and feed it through these values, and out comes the equation when you're done. And then you want to vomit and drink all at the same time. So we are not going to do that. We are not going to do that for a couple reasons. Number one, how many of you got a little bit upon seeing that, right? Number one. Number two, I could force you to do that, but you'll have no understanding what the hell you're doing because it requires calculus to even see why it's there. And even though I was taking calculus when I did it the first time, I didn't understand what the hell it was until years later when I went back and looked at it again. No. I gave you guys a handout last time, if you remember. Little booklets. Little booklet. I have more if you weren't here. I have more if you weren't here. I think I have more. I've got a couple here. I got 86 booklets here. I thought I had more. Did I give them all out? I must have. Oh no, here's some more. Now I had one TI-89 booklet. I gave that to the person with the TI-89. Who has a TI-86? Does anybody? No? Who has a TI-83 or 84 that didn't get one of these? I think I have just enough for everybody. Yay. Here we go. Here we go. One over to Ariel. Here we go. If you don't mind handing that back, Crystal, that'd be awesome. Micah, you need one. Benji, you need one. And, okay, there again. Tanner needs one. Look at that. Perfect. All right. So, here's what you're going to do for the next few moments. You're going to fold that little booklet into a booklet. You just did while you're ahead of the game, David. Thank you very much. Ryan. Or Ryan, whoever said that. I thought it came from over here. I know you're Ryan. I thought it was David. So you're going to fold that into a booklet. And when you fold it into a little booklet, you're going to keep this with you at all times because you're going to use this for the rest of the class. You got an exam, you bring this with you. You got any kind of regression homework, you bring this with you. Whether it's exponential, whether it's linear, whether it's quadratic, you're going to bring this with you. And eventually it'll become second nature how to use the TI to do this. But until it does, you got your little booklet. Okay? What is the title of this booklet?
Using the TI-82/84 to create a scatter plot and perform linear regression.
Boom! Somebody mentioned to me last time around in class when they saw this right here, they said, I don't have Excel, I can't make a scatter plot. I said, don't you worry. We're going to use the TIs to make scatter plots. So that's that. And then as far as that best fit line, the best fit least squares regression line, TI does that too for you. Okie doke? So your job over the next few moments is to guide yourself through this. Self-paced or with others, that's fine too. And then we'll reconvene at about 20 and we'll see what you come up with. Okie doke? So have at it.